Well, today is very nice. We're very happy to have Anna Maria Ray come tell us about dynamical phase transition in cold atomic gases. Professor Anna Maria Ray is a fellow of JILA, NIST fellow, and a professor at the University of Colorado Boulder. She's also received her PhD in Universidad de los Andes in Colombia, and she got her PhD from University of Maryland. She's won amazing awards, the MacArthur Fellowship, and the DEMA Thesis Prize, the Presidential Early Career Award for Scientists and Engineers, and a host of other prolific career. So we're very honored to have you here today, and we're looking forward to hearing your talk. So,
hello.
behalf of the audience.
Thank you, James, for the very nice introduction. I mean, it's a great pleasure for me to be giving the colloquium today. I'm sorry we cannot be in person, but at least I hope that you can learn a little bit, even virtually, of the work that we have been doing at JILA. Yes, so basically what I want in this talk is to tell you a story about ultra-cold atoms. And even though you don't switch fields and become an atomic physics theorist or experimentalist, I hope that at least I can convince you why we are so excited about this, the potential of these systems. All right, so let me start my talk by showing you these pictures of many body systems that I think we all will agree that really fascinating and useful: a ferrofluid, a superfluid, neutron star, binary star, and even the brain itself. Something that I want to point out is that, of course, they're fascinating, but when you think about how they operate typically, and you find them typically out of equilibrium. Not only that, but unfortunately, when we are dealing with many body systems, the issue that we face is the fact that they are extremely complex. So the point is that, as was maybe explicitly emphasized by Phil Anderson, a Nobel Prize in Physics in 1977, the behavior, hello? The behavior of a piece of matter is not just the sum of the behavior of independent particles. So what I mean is that even if we understand the behavior of a few systems, a few particles in the system, this will not necessarily allow us to predict or anticipate what is the emergent behavior when we have the many body system. And well, this applies especially when we are dealing with out-of-equilibrium systems that tend to be strongly correlated and entangled as the evolution happens. And moreover, in contrast to equilibrium systems, we lack the tools that allow us to describe the system in terms of standard statistical mechanics and free energy minimization. So the point is that what we're seeing is that this out of equilibrium many body system can exhibit very exotic behavior that actually is forbidden in many cases to exist at equilibrium conditions. And therefore, this is open a new potential for possibilities that we didn't anticipate before. And the question is that, given this complexity, but at the same time, these great possibilities, is there a way that we can understand the behavior of these complex many body systems out of equilibrium? And this is where ultra-cold atoms can play a role. So let me introduce them here. I want to understand or introduce what we mean by ultra-cold atoms, and can explain why we believe that these systems can shed a light in these complicated non-equilibrium situations. So for defining ultra cold, of course, I would need a thermometer. I need a temperature scale, and we know that, for example, at room temperature, about 300 Kelvin, the particles in the air are moving in the gas, the atoms, the molecules, like billiard balls. There are classical objects that are colliding and bumping into each other with a very fast velocity, almost moving at the speed of sound, 300 meters per second. And of course, these are very hard to control. These are too fast for us to travel and manipulate. So what we are going to do is we were trying to think how we reduce the temperature of these particles to reduce their velocity and control them better. And now, if I ask you to think, what are the most coldest temperatures that you can have in the universe itself? Then you might think, oh, it's the temperature of the outer space. And if I do a comparison of this temperature, that is a few kelvins, with, for example, the temperature at which helium condenses, that is also of the order of few kelvins, 4 kelvins, we realize that at this temperature, still the atoms are moving at a velocity of 19 meters per second, too fast. So one of the biggest accomplishments that we have realized in the last decade was the possibility to actually cool down arrays of 10 to the 4, 10 to the 6 atoms to very low temperatures. We were able to come down below 100 of nanokelvins to densities that are very dilute, like can be 5 orders more dilute than air. And at these conditions, atoms are moving very slow, at the order of centimeters per second. And under these conditions, we can trap and manipulate the atoms and use them for the exploration of the quantum world. Okay, this process it came as an effort of the community. So, and you can see it was not a single person, so it was the effort of many people. The first attempt to cool down the gases was using lasers, like to slow down the gases by light. And this was accomplished and recognized with the Nobel Prize of Steve Chu, Cohen Tanuja, and William Phillips. And they were recognized the Nobel Prize in 1997. And with that, well, we were able to reach microkelvin temperatures. But these were not enough, so cool them down the gas more. Instead of using lasers, you use the equivalent of an evaporation of a cup of coffee, where the hot particles escape and the remaining particles are colder. And that was applied to atoms by this Eric Cornell, Wolfram Ketterle, and Carl Wyman. And by doing that, they were able to cool down the gases below hundreds of nanokelvins in a regime where the temperature is cold enough that quantum statistics matter. And in fact, because they were dealing with bosons, they were able to reach temperatures below the critical temperature when the atoms form what is called a Bose-Einstein condensate. I will be explaining this a little bit better in the next slide. But the point is that they were able to cool them to this type of temperatures. They were recognized by the Nobel Prize in 2001. So as was saying, the idea is that when you have a gas and cool them down below a critical temperature, for the type of bosonic particles, they are very friendly and they try to all collapse to the same ground state. So that's where we're starting to probe quantum statistics. If there are fermions in steel, for example, here I'm showing you the case of spin 1/2 fermions. There is not actually a phase transition or something very sharp, but the particles start to stack into the minimum energy allowed by Pauli principle that prevents two identical atoms to be in the same internal state. So basically, the atoms are going to stack until an energy called the Fermi energy, that for me, I'm going to associate also the Fermi energy to the Fermi temperature later in the talk. And under these conditions, we are able to really get very cold gases, quantum degenerate gases, that allow us to explore a window for quantum and many-body behavior. I want to use this opportunity because it's unavoidable that when we talk about fermions, actually the person who pioneered cooling down Fermi gases is Deborah Jean. She was a JILA fellow, and unfortunately she died a few years ago, 2016. So I just want to recognize how much she has brought to the field. So in that regard, I want to say that the important point is that even though we are just dealing with atomic, molecular, and optical systems, what manipulating and controlling these systems is allowing us is to open a window to explore physics in other fields that go beyond what you might think just atoms would have been able to do. For example, we can connect the physics of atoms trapped in periodic potentials to the behavior of electrons in solids and emulate the behavior of Honde's matter systems. We are able to use fermionic atoms and bring them to very strong interactions that emulate the very strong interactions that happens in a nuclear star, and emulate a really phenomena of these extreme conditions. We are also, more practical, we are able to actually manipulate these atoms very accurate, and actually being able to create universal gates for quantum information. And finally, if we are able to bring these atoms to very strong interactions and emulate the physics of quark gluon plasmas under extreme conditions where they behave like an almost perfect liquid. So all what I want to say is that these systems, even though we are emo, are allowing to bridge the physics of very different systems and hopefully study the behavior of their complex, the emergent complex behavior. So what is our scientific vision? Our scientific vision is harnessing the behavior of these many-body atomic systems and use them for applications ranging from fundamental physics, but also for applications more practical, like quantum information and metrology. So basically, we're bridging the gap between the few and the many via quantum control, taking into account the fact that we have very well understood microscopics, in the sense that we can write the Hamiltonian of the system in a piece of paper. And actually, this is exactly the behavior that rule out the model without any type of additional imperfections. Second, and this is one of the key ingredients of my talk, we are going to be able to tune interactions, even dynamically during the course of the experiment, and access the quantum dynamics in real-time scales without the need, for example, ultra-fast probes. If we are talking about the tunability of interactions, something that I want to emphasize is that we can explore different types of interactions between the atoms. For example, we can actually use alkali atoms or neutral atoms in the first and second column of the periodic table, ground state atoms, and these guys interact via contact interactions. So you can imagine that they have to touch each other like hockey players when they're in a stadium in order to interact. On the other hand, we can excite these atoms to highly excited energy states. And in this case, we form atoms that interact via van der Waals interactions that fall into the distance as 1 over r to the 6. We can also have atoms, dipolar gases, that has distance, that interactions of the form of, that have dipolar coupling and decays with distance loss 1 over r to the cube. And moreover, we can go to the regime where we have, instead of hockey players, we have baseball players, and we have atoms, these are my atoms, that interact via the exchange of photons, and because of the photons can travel very far, these interactions can be almost all-to-all. So atoms in an array can interact with another atom very far apart at the same strain that an atom close to it. So we have the possibility to explore this full range of interactions, and what I'm going to tell you today in my talk is that not only that, but moreover, if we can make these systems of contact interactions under specific conditions emulate the behavior of these long-range interacting systems. So there is a lot of synergy between all the capabilities that we have. So, okay, so now I just motivated why these systems are interesting overall, and now let me go into the topic of this talk, that is the idea of dynamical phase transition and in general non-equilibrium phenomena. So I just wanted, before going into dynamical phase transitions, to point out that, as I mentioned at the beginning, that the advantage of out of equilibrium systems is that they offer the possibility to exist phases that have never seen before. And I'm giving you a few examples that came up in the last couple of years. One is the idea of time crystals, that are systems that are not only, okay, there is a chat, there is a question. If you can tilt your camera, oh, sorry. Let me see if I can do it. 1 second, my apologies. Is that better? Yes or not? Okay.
Looks better.
Just better? Okay. 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 Thank you. So I was saying that we were talking about new states of matter that don't exist at equilibrium, like time crystals. And these are systems that can oscillate and have a periodic behavior that lasts for a very long time. They not only violate the spatial, but also time symmetry. And we can have robust oscillations that happen forever in the presence of interactions in principle. We also have the possibility of having, let's see now, they having systems that even though that systems that are isolated, that are unitary systems that nevertheless thermalize and can thermalize very fast, emulating the physics of, for example, black holes that are the fastest objects in nature that thermalize. And there are other systems that actually cannot thermalize due to unitary dynamics. And all of these, this quantum thermalization and the modifiable localization can be characterized by the degree of entanglement that the system develops as a function of dynamics. So in when systems that thermalize, the entanglement grows very fast, whereas systems that have many-body localization, entanglement just propagates very slowly. So the other phenomena, so these are one of a few examples that you might have seen and you might have heard. But the focus of the talk today is the idea of dynamical phase transitions. So let me elaborate a little bit more on that. So, and with that, let me start reminding you what is an equilibrium phase transition. So, and I'm going to show you, for example, the phase diagram with water, that we know that a phase transition is described by an abrupt change of behavior of the system and non-analytic behavior as we change one of the system's parameters. For example, in the case of temperature, finite temperature or classical transitions, the parameter can be the temperature, or in the case of quantum system, it can be other parameters such as interactions, and these are called quantum phase transitions. The point is that these phase transitions at equilibrium are described by another parameter, and this order parameter changes non-analytically at the transition point. For example, if I show you the phase diagram of water that you might be familiar with, we have the temperature, we have the pressure, and we say that as we change the temperature, the pressure, then we have different phases, and the other parameter that have an abrupt change of behavior between the phases is the density. So we have ice, water, and water vapor. The point is that we can get these phase diagrams by initialization of the free energy, and we get them when the requirement is that the system needs to be at equilibrium all the time. So for going to here, I of course have to vary my temperature or my parameters very slowly, so the system always is at equilibrium. So now, when we go to the non-equilibrium scenario, then we talk about non-equilibrium phase transitions. They have very similarities, but are also very important difference with respect to the equilibrium ones. Let me warn you that the terminology of non-equilibrium phase transitions have been used broadly. So not all the people, there is no consensus. Sometimes people talk about different cases of non-equilibrium phase transitions, and the boundary is a little bit blurry when we talk about open systems. So for this talk, I'm only going to talk about closed systems that conserve energy, and the definition of the dynamical phase transitions is the existence of also another parameter that can be a time average or the behavior of long time, and this other parameter is going to distinguish two different dynamical phases that and features a non-analytic behavior at a critical point. So near the transition, we are going to expect to see the same scaling behavior remains that you find in typical conventional phase transitions. But well, so this is kind of looks similar. The difference is that these transitions can, of course, not be found by minimization of the free energy, and there are no symmetries that happens. For example, if you have an equilibrium transition and you change the sign of the interaction, immediately you are going to change the phases that you have. This is not necessarily applied to dynamical phase transitions, as I will show later. So there are no symmetries that apply. And most interesting, the reason why the community is interested in non-equilibrium phase transition is that it provides, hopefully, a way to generate entangled states in an easier way that we typically need to do if you were trying to do an adiabatic preparation of the entangled state. So, okay. So the idea, the concept of a non-equilibrium phase transition or dynamical phase transition, it goes back for many, many years. But the point is that only in the last couple of years, experiments are at this situation, at the position to actually explore these non-equilibrium dynamical phase transitions. For example, in 2018, researchers in JQI reported a dynamical phase transition in an array of 53 trapped ions. In this case, let me say, however, that 53 well, it's great, they saw the transition, but of course it's not a many-body system. And it's just recently, in the last couple of years, last year and this year, that we have been able to see dynamical phase transitions in genuine many-body systems. We are talking systems of 10 to the 5 million atoms, and those have been seen at Toronto and at JILA. And these two types of phase transitions are going to be the subject of my talk. One is it happened in fermions interacting via contact interactions, and the other happens in atoms interacting via the emission and absorption of cavity photons. So these are the hockey players, these are the baseball players. All right, so let me start by the experiment in Toronto. For that, let me give you a little bit more of the experimental details. What we have is a Fermi gas, Fermi degenerate gas of potassium atoms. They are trapped in a 3D dipole trap, and we have arrays of the order of 10 to the 4 atoms. They're not completely very, very cold, but below quantum degeneracy. So what we did is that we choose 2 of the internal levels of potassium to the hyperfine levels to encode an spin 1/2 system. And this is going to be our qubit, our spin 1/2 atom. And we are going to try to control a single qubit gates or between and interactions between these atoms via RF pulses and by applying magnetic fields. All right, so let me describe what we wanted to control and later what is exactly the experiment. So it happens, as I was mentioning before, that we are talking about potassium atoms, and these atoms interact via contact interactions, and these are my hockey players. And actually the strength of the contact interactions is set by a single parameter that is called the scattering length. And it happens that in these systems, we can change the scattering length, this is the vertical axis, by tuning the magnetic field. So it happens that we can make them interact at a specific magnetic field. We can make the interactions very, very strong. Very, very strong. And in this case, these are my very aggressive hockey players. We are in the unitary limit. And just to connect with what was mentioned at the beginning of the talk, this is where my fermionic atoms can behave similarly as quark-gluon plasmas and also connection to high temperature superconductors. So this is a regime where the system really is truly strongly interacting, and the attentions of the community, because of these very exciting connections, have been focusing in that regime. So what we did was go explore a very different regime. We were exploring the regime of very weak interactions, very close to the zero crossing, when the atoms are mostly weakly interacting. This is the case of just really relaxed hockey players that are distance apart. And what we wanted to observe is what is different in this system when we change interactions. The surprising part is that even though we are in the very weakly interacting regime, still interactions can play a major role. So let me tell you why. So actually we see that as you tune interactions, you observe a dynamical phase transition. So I'm going to describe you exactly what type of dynamical phase transition we observe. In that case, the transition was characterized, or the order parameter was characterized by the total magnetization of the gas. So let me tell you a little bit how we measure it, and then where the basic idea. So what we have is that we start with a spin polarized gas of fermion atoms. These are all spin down, and because of all spin down, Pauli's exclusion principles make them no interacting. Then what we do is that we apply what is called a pi-half pulse. That is, we apply an RF light that creates a superposition between 50-50 superposition, coherent superposition between ground and excited state. So this can be visualized in a block sphere that points down if you have in the ground state, point up if you are in excited states, as a vector that is in the x direction. That is, you can see it's a superposition of excited and ground state and have maximum coherences. So in the initial state, you have a magnetization that is maximum and pointing along the x direction. After that, we turn off the pulse and we let the atoms freely evolve under the interactions or non-interactions, depending on how we set the parameter, the scattering length. And if we're a single particle, for example, in the presence of a magnetic field, for example, the spin is going to precess and accumulate a phase. And the idea is that we can understand what is happening of the magnetization and, for example, the phase that is accumulated of the rotation by applying another pulse, convert this phase, accumulated phase in the XY plane in population, and read the population by doing an Stern-Gerlach pulse that allow me to measure the number of spins up and the number of spin downs. So that measurement, hopefully, I'm sorry if it's confusing, hopefully it's not so, but for the non-experts, what I'm saying is that this technique is allowing me to measure the total magnetization of the atoms. That means I'm going to define, and this is going to be important for this talk, an spin that is the collective spins, that is the sum of the spins of each individual atoms and has coordinates x, y, and z. And what I'm measuring after this protocol is actually the length of my spin, of the total magnetization. That's the order parameter of this transition. So let me explain a little bit better what it means. So I started for that. Let me start with the non-interacting case that hopefully is much easier to understand. So what we have is an array of atoms that are trapped in an harmonic potential. Yes. So you know that in quantum mechanics, if you have an harmonic potential, that you have a set of quantized energy levels, the energy is quantized. And if we are cold, then you are going to start populate all these different levels up to the Fermi energy. Okay, the key here is that in the experiment, the particles in a spin up and down feel very slightly different trapping frequency. And as you remember, the energy of the atoms is proportional to the trapping frequency. So the spectrum of the up particles is slightly shifted from the spectrum of the spin down particles because of this difference in trapping potential. So if I'm going to describe the behavior, the dynamics of these atoms in these single particle potentials, so you can see that the atoms, if I prepare the atoms in these energy levels, because of definition of energy levels, the atoms are not going to, the only thing that they are going to do is they're going to acquire a phase. That means the dynamics of the system is kind of, it can be mapped. So if I have an atom and I just model it as a spin up and down, what happens is that because the energy difference between the spin up and down, then the dynamics is just can be written in terms of Pauli operators, Pauli matrices, sigma C matrix, and with an coefficient that is the difference between the energy of the up and down particles that is set by the difference in trapping frequency. So because the harmonic oscillator energy depends on linearly with the mode, so what happens is that we have particles that has a slightly different energy. So you are saying a bunch of spins, each one with a slightly different energy or effective magnetic field, and therefore each one is going to precess as a different frequency. And we can tune this magnitude of this HI by controlling the inhomogeneity, the delta omega. So if we look at the dynamics, if I start with an array with all the spins pointing along the x direction, then what happens is that as the system evolves, because some atoms evolve fast, some of them evolve slow, then if I look at the total magnetization, what is going to happen is that the gas is going to very quickly depolarize. So if this is a plot of the total magnetization versus time, after 100 milliseconds, the experiment sees that the magnetization decays because the system dephases. The solid line is a theory line that reproduces the magnetization of the gas. And I mean, it's just, the physics is just dephasing. The other way that I want you to understand this physics, because it's convenient when I introduce interactions, is that when you have an spin system of many spins, you can either use the decoupled basis, like SI, or you can use the coupled basis. So we can define these collective operators that are the sum of the individual spins, and these collective operators have eigenstates. The eigenstate of S squared is SS plus 1, whereas this is the total magnetization. And the point is that this Hamiltonian doesn't commute with S squared. So this H and this S squared do not commute. So what happens is that I start with a gas that is completely polarized along X, as I write in here. Each spin is pointing along the same direction. Now I let it evolve, and because total S is not conserved, what happens is that as a function of time, the difference, because of the variance of these HIs, the system is going to demagnetize to different S sectors until the majority of the atoms in the 0S sector, that is where is shrinking the length. So this corresponds to the case when the magnetization goes to 0. Is that clear? Okay, so hopefully, I mean, if you have questions, please interrupt me. I tend to go fast, so please ask questions if you have them. So now let me try to go from this simple picture to try to add also.
So, Anna, may I ask a question here?
Sure.
Why does SZ and S squared not commute in this case?
Remember, this total S is the total, and this SC is individual spins. So total S is going to commute with total SC, with the total, but not with the individual spins. Remember, in the coupled basis, the individual spins doesn't commute. So total S commutes with total SC, and of course the number of excitations remain constant, but not with SI, within the individual spins. Yes?
Yes.
So that's the problem. So I'm going to, unless if the HIs were exactly the same, this will be total S, and then they will commute, and the system will not magnetize because all the spins are going to oscillate together. All right, so let's try to see what is the effect of interactions. So first, you might imagine that this could be a very complicated problem, even if there is weakly interacting, because you have atoms that are mobile particles in a trap that are having interactions. So in principle, it's not that trivial to model. But if the interactions are weak, as in the regime that we want to operate, then one important point is that we are going to operate in the regime when the interactions are weak enough that because of the interactions, two particles collide. When they collide, they cannot change the single particle levels because it costs too much energy. So the interactions is weak enough to prevent the particles to populate different harmonic oscillator states. In this regime, what the effect of these interactions is not to change modes or thermalize. The effect of the interactions is just introduce spin flips. So an atom can remain, as long as they remain in the same harmonic oscillator levels, they can flip between spin up and down with very small energy cost. And that's kind of the physics that we want to model. So we are going to have then the physics where the atoms remain frozen in this lattice size that are in energy space. So these are mode oscillator levels, and X, Y, and Z. Atoms remain in this single particle eigenstate without motion, but what they do is that they can flip-flop. And in fact, if you think about what is the effect of the interactions, because the atoms are interacting only by contact interactions, only when they touch to each other. Nevertheless, an atom in an eigenmode here is completely delocalizing the trap. So an atom in this mode can actually interact with any other mode because the atoms in these modes are delocalized. So that means that interactions actually become long range in this energy space. We don't have mode changes, but we have interactions that can flip the spin. And actually the Hamiltonian that describes the interactions is what we call a Heisenberg model. This is of the form S dot S. This means S dot means is because if you can think about this, the triplet, if you consider two particles, the triplet, only the singlet interact. The triplet cannot interact because spin polarized atoms cannot interact via S-wave interactions. So the Hamiltonian is the form S dot S. The state of minimum energy is the polarized state. So that's why this is the minus sign. And in this Hamiltonian, this strength of the coupling constants is not short range. Actually, it can be very long range. These coupling constants are determined by a strength that is set by the scattering length. That is what I mentioned before. We can control with a Feshbach resonance. And the amplitude is going to be between mode I and J. Is just going to be the overlap between the modes square. And this function can be quite non-linear, very long range. So what we are going to do is trying to understand what adding this term adds to the dynamics. And the point is that this term adds a gap protection and wants to stabilize the initial polarization of the alignment that initially we introduced to the gas. Because in this basis, total S is a good basis. This basis connotes with total S. And what happens is that it not only connotes, but actually, because of this term exists, there is an energy difference between states with S equal to n half, and for example, n equal n half minus 1, and so forth. This gap is large, is proportional to n. The mean of the coupling constants for harmonic oscillator levels is proportional to A divided by the square root of n. So this gap grows as a square root of n for an harmonic trap. And what happens is that if these single particle terms that wanted to depolarize my gas very quickly now has a huge energy penalty, and therefore the spins don't want to depolarize. So this stabilizes alignment and serves as a gap protection. So that idea, well, of course, is not new. The idea that S can stabilize alignment has been, we worked even when I was doing my PhD, my postdoc actually at Harvard. So let me give you another picture to understand this alignment, because sometimes it's good to have two different pictures. The other picture is trying to go to a mean field model where the effect of the interactions of their particles is to generate an effective magnetic field over my spin I. So my spin I interact with other atoms, and the other atoms just generate a magnetic field. And in this case, the magnetic field, besides the local field from individual particles, there is the interactions that are a local field in the direction of the block vector of the spin, all the particles. So, and therefore, this term imposes an energy penalty and wants to make the spins align all to each other. So this effect, in this type of induced spin alignment, can also is sometimes termed identical spin rotation effect, and were explored, for example, in rubidium magnetometers. So the important part is time dependent, because it's the evolving spin magnetic field generated by other atoms that favors alignment. So basically, if I want to give a cartoon, if I have only two atoms, for example, and they have different frequency, if they're not interacting, they're going to depolarize at a rate. You see the blue arrows, they're going to depolarize. Whereas if I have interactions, the interactions want to make the atoms align. Actually, the dynamics might be a little bit more complicated. They do circles around the collective spin, but they want to maintain the magnetization, the total alignment. So this physics, actually, is exactly the same physics that people in condensed matter use to model the behavior of superconductors. And we actually, what we are doing is that we are going to use the formalism developed by condensed matter theories to actually tackle the problem. So where is the connection? The connection is that if you have a superconductor, you have the interactions, you have attraction, then you want to form holes, or the fermions want to pair into Cooper pairs. That's the low energy states, either to form a hole or to form a Cooper pairs when you have momentum spins up and down. It's a singlet, for example, of two atoms with K and minus K. So because the Cooper pairs have different kinetic energy than the empty sides, then you have a term in the Hamiltonian that is, this is momentum space K, a Hamiltonian that is AK sigma C. This is the kinetic energy of the difference between kinetic energy of a Cooper pair than a hole, because the hole doesn't have any energy. And then the interactions, what it introduces is that they want to, this sigma minus operator, what it happens is that destroy a Cooper pair and generates an empty side. So the interactions have the form S minus S plus. The interactions are also all to all range, because they are in momentum, so they're all to all. And they, in condensed matter, the order parameter is defined by the expectation value of the collective S minus. This is defined, this is the gap function, the order parameter of a superconductor. So this is exactly to the Hamiltonian that we have. And in fact, this Hamiltonian at the mean field level is integrable and is called the Richardson-Gaudin model. And in condensed matter, they have derived actually formalism, that is called the last construction, to actually exactly solve the dynamics until this equation. And there has been a lot of predictions of different phases, dynamical phases that you would have if you were able to quench a superconductor. So change the gap from one to the other value abruptly, and then try to look at the dynamics. So in fact, if I point out, there has been many papers that have been trying to tackle these different phases of superconductors, a lot of theory work, but unfortunately, experimental work very little, because it's very hard to quench a solid state system, and moreover, you need ultra-fast probes to observe the behavior. So there has been some evidence of some behavior, but only very weak quenches. On the contrary, we can model large quenches and actually see the physics in real time. So that's the dynamical phase transitions that people have predicted in superconductors. So as I said, the order parameter is S minus, and this minus have characterized by a magnitude and a phase. If the interactions are weak, then what happens is that this single particle term wins and the system depolarizes. So the total magnetization at infinity is going to be 0. However, at some point, gap protection wins, interactions want to align, there is a sharp transition, and at long times, there is the coherence build up and the system remain aligned. For very strong interaction, the system remain aligned. Similar abrupt behavior is observed in this phase that of course is not defined when you have decay, and then at some point, this phase is going to grow in this form predicted, and the analytical behavior of the phase and the magnetization actually are analytic functions that you can construct. I mean, in this case, we don't have to worry about the details, just the fact that it's a sharp non-analytic behavior and two phases, phase 1 depolarization, phase 2 alignment. So that's what we wanted to see in the lab, and this is what they observed. So we look at the total magnetization versus time. If we have the interactions very weak, we see that as a function of time, it decays. The theory line are solid lines, the experimental points are the dots. The theory line are just solutions of these mean field equations. As we increase a little bit the interactions, what happens is that we see almost the same demagnetization, not too much different, but at some point, abruptly the systems start to magnetize and remain aligned, and the oscillations start to happen, and until you get a phase where you are really stable. And if you characterize the magnetization versus interaction strength, you see that there is no interactions, if for weak interactions, no magnetization, and suddenly it builds up. Points are experiment, the solid line is the theory, including the fact that we don't have all-to-all interactions because it's a magnetic trap. If we had all-to-all interactions, there would be also a transition. This is the simple mean field model that we can analytically solve from the LAX construction. So there is, however, in both cases a phase transition, and both in the magnetization and in the phase, we can see there is, of course, phase is not defined here and start to grow as a function of the interaction. We can not only start this part of the phase diagram, but we can also explore how the gap protected regime or the unpolarized regime changes as I change the variance of my coupling constants. So the larger the variance, the longer the unpolarized state remains stable. So as here, you can see this is the inhomogeneity. As I increase my inhomogeneity, the unpolarized phase grows. And this is as a function of the interaction. So for example, these are cuts for different invariant inhomogeneities, and you see that, of course, the line shrinks for smaller inhomogeneities, and we can also do some vertical lines we can be at weak interactions where the system demagnetize for all the inhomogeneities that we have, or we can go to a very strong interaction where the system remains stable. Like this is stable, this demagnetized, and then this is a boundary between demagnetization and stabilization. Depends on how large is your edge. So for a small edge, then you have a stabilization, but for large edge, you have dephasing. So we were able to explore the dynamical phases and actually observe them in a very clear way. And this line here is the line that I showed you in the prior plot. So with that, let me start briefly and stop. And if I am allowed, I want to tell you a little bit of the other type of phase transition that we see. But before I do that, I want to see if there is any questions about this experiment. Okay, if not, then let me move forward.
On behalf of the, yeah, yes.
Oh, okay. Mm-hmm.
That's good. I was just going to say thank you. Please keep going.
Okay, perfect. Okay, so now take a breath, and now let me try to connect briefly about the other. I mean, I talked to you about hockey players, atoms interacting via contact interactions. Let me tell you a little bit about baseball players, trying to see how they behave and how they can behave very similarly. So the atoms that I'm going to work here are strontium atoms that work in the second column of the periodic table. And therefore they're alkaline atoms, and they're very nice atoms because they have a very long-lived excited state that can live for more than 100 seconds, because this transition is optical, it's both dipole and spin forbidden. So I have a state that have lived for very long time, very narrow recombination line, and this is why these atoms are ideal for clocks. In fact, they have a quality factor that corresponds to a pendulum. I mean, it's quality factor of 10 to the 17, the ratio between the vibrational energy and damping. So the energy difference, this energy splitting that is optical compared to the damping that is just only millihertz. Very long lifetime, and this factor can be as long as 10 to the 17. So it's a pendulum that would, when it's set to swing, would have swing for the entire age of the universe. So these are why these atoms are so fantastic, and this is the basic of atomic clocks. So, but we are going to use these atoms in an optical cavity. So we are going to use the cavity, and you can see that because the damping is so small, so slow, the cavity damping is always what it dominates. So the cavity damping is normal, it's the order of few kilohertz, but it's much more 9 order of magnitude larger than the actually decay rate. The cavity photons, actually what they can do is that they mediate interactions between the atoms, and these interactions are completely collective because they are localized in the cavity. So in photons in the cavity, they mediate exchange interactions of the form J plus J minus collective, with a magnitude that depend on the detuning of the cavity mode respect to the atomic transition. And we have also a dissipative term that because it emerges because the photons decay with a rate kappa. So let me concentrate here in the exchange interactions. These are, you can see that these are coming from the virtual interactions mediated by photons. An atom in the excited states go to the ground state. This photon emitted is absorbed by the other atom and goes to the excited state. So this is J minus J plus term. It's collective, and as I said, is proportional to the cavity detuning, more or less. And these kind of exchange interactions are not, of course, characteristic of only cavities, but we saw them in the atoms that I just said, but also there are many systems that have also different type of exchange interactions. So these are collective, so that's one interesting part. So I don't know if you found very exciting, but I told you in the Hamiltonian that I showed you before, we have atoms interacting via contact interaction that have that exhibit a collective S plus S minus term. I mean, for this system is kind of natural because the exchange is mediated by photons. So this X plus S minus term can also be associated with a gap protected term, J squared, and something that is collective JC squared. The JC squared is a term that is known to give rise to what is called spin squeezing, one type of entanglement. But on this term here, J squared, this is the same that we had before, is the gap protection that we explored in the prior experiment. We tried, the idea is that if we have inhomogeneities in my system, then the idea is that this gap protection is going to prevent the dephasing, and therefore trying to facilitate the generation of spin squeezing. The problem that we had, however, is that superradiance, because the decay of the cavity in these systems is quite strong. So in order to see pure unitary dynamics, we would have to detune the cavity very largely and making the time scales very slow. And then we are subject to other sources of decoherence. So in order to see the transition, we went instead and explore another slow transition, not the clock transition, that is between 1s0 and 3p1. And what we did in this case, we could operate in the regime when gamma divided by chi, when the elastic interaction really won compared to the superradiance, so the spontaneous, collective spontaneous emission. And we actually, what we did is to drive the cavity. So what we have is a system where we have the exchange interactions mediated by the cavity, and we have a collective drive, and we can also add the tuning from the pump to the cavity, and this is a collective JC term. So this model is called the Lipkin-McCulloch model. It's a collective spin model, is simple, and this also exhibits a dynamical phase transition, and also the magnetization along C is the order parameter. Here is the phase diagram. It's a little bit more complicated. You have the detuning, you have the transverse field, and you have, and we are normalizing by the interactions, and then there is, for very strong, I mean, for example, if we are going to have at zero detuning, for very weak drives, then the spins want to remain in the south pole, so JC remains almost -1, and at some point, the drive wants to introduce rotations, and the spins start to rotate in the YC plane, and therefore, in this case, the rotations, on average, the magnetization is 0. So what happens is that you go from a paramagnetic phase that it has 0 collective magnetization to a ferromagnetic phase where the spins align. And this phase, actually, phase diagram has us also, I mean, so a transition and then a small critical line, very similar to the water phase diagram. It's a little bit complicated, but the important part is that there are two phases, a ferromagnetic, a paramagnetic, separated by a critical point that can happen, and also happens as you change the tuning. What we did was trying to explore this phase diagram and this dynamical phase transition. For example, at 0 detuning, when you have very strong interactions, the magnetization remains mostly along the C direction. So we start along C, and as a function of the dynamics, you remain aligned. These are comparison between theory and experiment. As you try to increase your drive here, we see that we start to develop some oscillations still confined to the south pole. And then as a critical point, you are going to have these oscillations that are going to persist. I mean, we have some damping here because we have inhomogeneities in our system, but you can clearly see that the system goes above the North Pole and keep oscillating. This is kind of, you can understand this kind of at the time average, because the time average goes to 0 as expected in the paramagnetic phase. We see and explore the phase transition as a function of the particle number, and we see that for different particle number, we can collapse of the lines to a single one almost, described by this, and this is the solid line, is the theory, so we can see the transition between a ferromagnetic to a paramagnetic where the order parameter vanishes, and as a function of different atom number. And we can also do cuts along the horizontal part of the phase diagram, not only on the vertical. So here, as we change the detuning, if the system were not interacting, we have just the characteristic Rabi chain. But here, because of interactions, we see this very sharp, non-trivial line shape that has this abrupt discontinuity as we go from the ferromagnetic, when the magnetization remains or -1, and abruptly it goes to the paramagnetic phase. And then for very, very long, large detunings, then of course, for very large detunings, the system, it's just becomes single particle and oscillates. I mean, you just get the trivial zero magnetization. But the important point that I want to emphasize is that we see similar behavior even when the sign of the interactions is changed from positive to negative, just the line changes. This is very different from equilibrium phase transitions when you change the sign of the interaction and very different behavior emerges. So this is along this, in this case, I'm showing along this horizontal line here where the drive is not that strong compared to the interactions. If we go to very stronger drives, we go, this is this. So when we go to stronger drives, we go and explore more single particle physics. We can see that the single particle line shape behaves very similar to what we observe, although we see still some sharp behaviors for the two signs of the interactions. So we can see features of this transition. So I'm just to finalize, and I'm just running out of time. Hopefully I can convince you that dynamical phase transitions are interesting. They have different behaviors that are not shared by equilibrium phase transitions. What I didn't show you, however, is that I told you that this should be useful for generation of useful entangled states. Unfortunately, so far everything has been done at the mean level, but our hope is, however, that we were trying to explore and so the hope is that this clock has now coherence times that exceeds 12 seconds. So hopefully we can use this Fermi gas in order to see similar type of phase transitions to the one that is in the prior, at the beginning of the talk, but with much more longer coherence time. And with that, let me just finalize and really thank, of course, my theory team and the members that actually work on this, on doing the calculations, the Toronto team with Joseph Wilson, and he's the one who did all the measurements for the transition in Fermi gas, James Thompson, and he's a group of postdocs and graduate students who do the measurements for the dynamical phase transition interactives. And during I didn't tell you detail, but we are exploring this dynamical phase transition in his talk. And with that, well, just hopefully you can see that there is a bright, and hopefully you can use ultracollapse to explore not only quantum simulations of synthetic materials, but hopefully quantum.
Excuse me, Anna?
Yes.
I think there's some difficulty hearing the last bit of your talk. Is it possible just to repeat a little bit? Because it was a bit hard to kind of some static on the line.
Okay, sorry. So where these slides of this acknowledge is okay? Or
it's sounding good now. You can go from I think here the next slide. I think it's okay. But
in the
I think just to clear up the sound.
Yes, perfect. I just wanted in these slides to say that I believe that there is a great vista ahead, and so far we are using these atomic systems as quantum simulators. But hopefully this is just starting to build more exotic synthetic materials, and hopefully even quantum computers, and develop better quantum technologies. And with that, well, thank you very much for your attention. So let me stop sharing.
Thank you very much. This was a fantastic talk. I think I learned a lot about mean field, and just hearing a lot about all these things is very interesting and nice to see how these things are put together. Let's see if there's any questions from the audience. Okay, here we go. It says, what is it about strontium atoms that give, well, let's actually, can we actually enable, yeah. It says, I'm sorry. So the question is, what is it about strontium second column atoms that give them such a high quality factor?
Yes, so the reason is that these atoms have two valence electrons. So the ground state of these atoms have J equal to 0 states. So the lowest energy state has a J equal to 0 state, and the first excited state is also a J equal to 0 state, and 0 to 0 transitions actually are forbidden in principle. So this transition is only allowed because you have nevertheless the nuclear spin that introduces some hyperfine coupling that makes the transition not allowed, but is the fact that it's this very J equal to 0 effective J equal to 0 transition that is dipole and spin forbidden. So basically it's the two outer electrons that doesn't happen in alkali atoms that have J equal to 1/2, and therefore you can have a direct dipole allowed transitions.
Thank you. That's very interesting. I didn't know that.
Okay, we have another question. Let's see, Miles. Well, let's see if we can let him ask it live. Let's see. Okay, Miles.
Yes, superradiance is interesting on its own right. I fully agree. Not for unitary dynamics that we wanted for these phase transitions, but actually the competition between drive and superradiance generate even other type of non-equilibrium phase transition. And this is something that we are exploring now. So in James' experiments, they have seen already signatures of superradiance, very clear, very nice signature. This is easy to observe. One of the prospects of these narrow transitions and this very strong superradiance is that this is the initial point for what we call a superradiant laser that can be very stable because the line width of the atoms is much more narrow than the cavity decay. So I fully agree. I fully agree. The point is that for this particular case where we wanted unitary dynamics, superradiance was very bad.
Thank you. This is Miles. You answered my question. Thank you very much.
Okay, see if there's any more questions. Okay, let's see. Give everyone a second. Otherwise, let's say thank you very much for the wonderful talk. After this, we have a coffee hour after this, where we're gonna have everyone join to just have a few moments to discuss a little more informally and have a virtual coffee break as much as you can. This was a fantastic talk. Thank you very much for enlightening us about some of the cutting edge atomic physics and molecular physics. So thank you very much.
Thank you.